So, welcome back to our video lectures on projective geometry. We are dealing with Cayley Klein geometries, and the reason for that lecture is I want to give you the big picture, how different Cayley Klein geometries fit together to form, well, I would say a big system of geometries where all the puzzle pieces fit together in a kind of smooth way. And for that lecture we will need many things of what we did so far. We will need our classification of the conics into primal dual pairs. We will need the classification of the measurements into elliptic, hyperbolic, parabolic measurements, both for angles and for distances, and we need the entire projective setup and projective classification up to projective invariance. So in a certain sense, this lecture is the high point of the second part of our projective geometry class, because it will tie together all the pieces, all the different threads we have been working on in our past lectures. So the fundamental question I want to deal with in this lecture is which types of fundamental objects lead to which kind of Cayley Klein geometries. And I promised you to give you the big picture, and here is the big picture. So I decided to put everything on one slide, and you see a big table here, and you see our different types of primal dual pairs of conics, and we somehow will have to relate these here to the different types of measurements in that table. And you see it's very dense, and I wanted to show you where we are heading at, but I want to develop that piece by piece. So let's first see what is this table about. You see 9 fields in that table, and I want to fill in these 9 fields, and these 9 fields correspond to measurement types of distances and angles. So you remember, distance measurement could be either hyperbolic, elliptic, or parabolic, and similarly the angle measurement could also be hyperbolic, elliptic, or parabolic. And what we want to understand is which types of fundamental objects lead to which types of measurements, and everything up to projective transformation. So here is a list of the 7 types of primal dual pairs of conics. So you remember we had this case here, which was our picture for having a non-degenerate real conic. So this picture here covers ellipses, parabolas, and hyperbolas, and they were all related just by projective transformation. So whenever you have a non-degenerate real conic, you can apply a projective transformation and end up with a picture that is essentially just equivalent to a circle. We had one other non-degenerate case, which was the only complex case, the case where you don't see anything in the real projective plane, where all the solutions to these quadratic equations are essentially complex. And then we had all the degenerate cases. So we had, for instance, a case of 2 lines intersecting in one real point, and those 2 lines came in 2 different flavors. They could either both be real or both be complex, and we had the dual situation of that double line with 2 points on it, and this pair of points could either be real or complex conjugates. And then we get this kind of double degenerate case where we have a double line and a double point, both of them real. And there are 2 things that should jump to your mind at that point. First thing is that these cases we have here, the collection of primal dual pairs, somehow resembles what happens here with our measurements, hyperbolic, elliptic, and parabolic, because you see, well, you have this distinction, both real, both complex, meeting in a point. This really corresponds to what we have here in the elliptic, hyperbolic and parabolic case. Second thing that should jump to your mind is the following. Here you have just 7, and here you have 9 possible combinations. So already now you see it will not be a one-to-one mapping what we are getting, but it will be kind of one-to-many mapping. So some of these entries here will occupy several spots in the table here. So now I want to step by step fill the entries of our table by step going through the 7 types I have here. And I will start with this field here in the corner, not because it's very important in the aspect of the entire theory, but this is the type of geometry we are really used to. Here you find Euclidean geometry, and the question is, where do you find it here in the table? It is this field where you have a parabolic distance measurement and an elliptic angle measurement. So let me explain you why this happens. Before that, let me introduce equations for the primal and the dual conic. So the primal conic should be this double line here, and I put it at z squared equals 0, so it will be a double line at infinity in the standard embedding. And the dual conic, I chose it in a way such that the 2 points on the double line will be exactly I and j that we had when I introduced the projective setup for Euclidean geometry. And now let's look how distance measurement and how angle measurement looks in that geometry. Let's first start with distance measurement. So you want to calculate the distance between 2 points. What do you have to do? You have to form the join of these 2 points. You have to intersect it with your fundamental object, and in that case you just get one intersection, since this line at infinity here was considered as a double line, so we just have one line that forms the whole primal part of the conic. So you have a point P, a point Q, and X and Y coincide, so you end up in a parabolic length measurement where you cannot measure absolute lengths, so the absolute Cayley Klein measurement would be just 0, but you can compare distances to unit lengths, like say the length of this pencil here, and with respect to that measure other objects in your universe. And you see, if you walk in unit steps towards the line at infinity, you will approach it if you walk in one direction, and you will approach it also if you walk in the other direction. So it is as I told you in our introduction lectures on Euclidean geometry. So how about angle measurement? So if you want to measure the angle between 2 real lines that intersect in a finite point, so the point of intersection should not be on the conic itself, what do you have to do? Well, first you have to take this point of intersection and draw the 2 tangents to the fundamental object, but in that case the tangents have to pass through your 2 special points. You remember when we were introducing polars of conics, we learned that if you have a degenerate conic consisting of 2 points, then all tangents will automatically pass through these 2 points. So what we get here is we get 4 lines through our point here. 2 of them are complex conjugates, 2 of them are real. We have to calculate the cross ratio, and since these 2 lines are complex conjugates, we get an elliptic angle measurement. Actually, the way I chose my objects here, my 2 special points here, play the role of I and J. Literally, they are at the position of I and J. So we completely understood what's going on here. So if we have points that are not on the line at infinity here and lines not intersecting at the line at infinity, our Cayley Klein measurement really gives us exactly the formulas for Euclidean geometry. So we can say this is Euclidean geometry, and we completely understood that case. So how to proceed? Let me proceed with a case that is in a sense a very close relative to this one, the case in which we care about this entry here in our table, where we have a double line and two real points on the double line. And you already may imagine where this is located in our table, because here we had two complex conjugate points on the double line, and this led to an elliptic angle measurement. Now we have two real points on the double line, which will lead to an hyperbolic measurement. So what do we get? Let's again first write down the primal and dual fundamental conic. The primal conic is still our double line at infinity, and the dual conic is represented by x squared minus y squared, which gives us two real points at 1, 1, 0 at the line at infinity and 1, minus 1, 0 on the line at infinity. So how is distance and angle measurement in that case? Well, distance measurement is similar to what we get in that case. If we take 2 points and walk in unit steps, we will approach this line at infinity, and we will approach the same point no matter in which direction we walk. The angle measurement now is different, because this time we have our two lines where we do the measurement, and we have two real tangents to our conic, which leads us to a hyperbolic angle measurements, which means if we add angles of the same type, we will get closer and closer to this limit line but never surpass it, and if we do it in the other direction, we will end up with the other limit line here. I have to do a few remarks at that point. So first of all, what I did here is a classification up to projective geometry. You may projectively transform this image or that image to a situation where the double line takes any possible position in your projective plane, and your complex conjugate points here are at any possible position. Similarly here, but with a projective transformation, you can never get from that case to that case, at least as long as your projective transformation is a real projective transformation. So projective transformation with a matrix consisting just of real numbers. So in the same way as we classified primal dual pairs here up to projective transformation, this here is a classification of geometries up to projective transformation. That was the first remark. Second remark, you have seen Euclidean geometry is relevant because it covers a kind of real-world case. So it covers our Euclidean type of geometry. And so is this case here. It covers a case that is extremely important. And now you may be surprised by the name I will give to that. I call this relativistic geometry, and it has a lot to do with the geometry that you end up when you do the theory of special relativity from physics. So what does this have to do with physics and special relativity theory? I could give an entire lecture just about this geometry and what it has to do with relativistic geometry, and here I just want to give a brief hint in that direction. So you may have heard about Einstein's theory of special relativity, where you measure the speed of objects in different coordinate systems, and you may remember that it is impossible to go beyond the speed of light. So there is nothing faster than speed of light. So if you for a moment think of something like a railroad track, and on that railroad track you have a train. So this here is a train with several things attached to it. It has a relative speed with respect to that railroad track. And if on that railroad track you place another railroad track, and on that railroad track another train which also has a certain speed, and you iterate here, and at the end you measure the relative speed of your first railroad track here to your nth train up here, this speed will never be faster than the speed of light, which is very counterintuitive because it seems like we are adding speeds, but we never go beyond a certain limit speed. And actually the lines that you saw in that picture here, they correspond to diagrams of moving objects, and the fact that you cannot add speeds in a way that you surpass a certain speed of light corresponds here to the situation that adding angles you cannot get beyond a certain limit line which corresponds to a certain speed. So this is really a very, very rough sketch of what is going on. So essentially angle measurement in that picture here relativistically corresponds to speed measurement. So let me continue with even one more degenerate case. So we understood this one, and let's now move to this situation here where you have a double point here. And in that case, both the length measurement and the angle measurement, both is parabolic. So you get a double point of intersection for the length measurement, and you get a double tangent here for the angle measurement. And this physically corresponds to a situation where the speed of light is infinite, and the name for this kind of geometry is actually Galileo geometry, so corresponding to a classical theory of physics where you assume that the speed of light is infinite, and actually you can really understand how relativistic theory is a kind of situation where, as a kind of limit case, when you make the speed of light faster and faster, ends up in a classical theory. So you don't have to understand the physical implications, but you should understand how these cases here fill the parabolic distance measurement column in our table here. So how to proceed? So far we understood three cases. Let's, as a next interesting part, jump to the only complex case. This sounds a little bit of weird because I postponed the case that corresponds to the most natural conic to the very end somehow, and you will see why I did that. Let's first focus on the case where I have only complex primal and dual solutions for the conic, and this occupies this part of the drawing here of our table where we have an elliptic measurement both for angles and for distances. And so let me first give you the two equations of the primal and the dual conic. Here I've picked up to projective invariance two representatives that fit together. It's something like x squared plus y squared plus z squared equals 0. So in our usual real projective planes, there are no solutions for that. You remember we excluded explicitly the 0, 0, 0 point for homogeneous coordinates. So there are no real images, neither for the points nor for the tangents, that you can see here. But still, you can do the calculations. And if you do the calculations, what you end up with is the following situation. You have 2 points with respect to which you want to measure the distance, and you want to, say, walk in unit steps here. What is the intersection of these 2 points with our primal conic? Well, it's intersecting the primal conic in 2 complex conjugate points. So we end up with an elliptic distance measurements, where if we walk in unit steps, we go on and on and on. At some finite point, we will come back again on that line from the other direction. And similarly, we have the angle measurement. If we have 2 lines here that intersect, then we can take the tangents at the point of intersections to the fundamental conic. We will get 2 complex conjugates, and we will end up with an elliptic angle measurement. In that case, both angles and distances are elliptic measurements. And this may sound like a little bit well, unnatural situation, because you do not see the conic in that case. Actually, it's not that unfamiliar. Imagine the following situation. Imagine a sphere in 3-dimensional space, and imagine you being a living person on the surface of this 2-dimensional surface of this 3-dimensional ball. And if you walk in unit distance in a certain direction, what will actually happen? You will walk in a big circle on your sphere and eventually come back to where you started. And if you measure the angle between 2 lines, you can just take the angle measurement on that sphere. So essentially, this situation here almost represents the situation on a sphere in 3-dimensional space. And I have to say almost, because there is one little and important twist here. So this sphere here represents our entire projective plane, our RP2, embedded on the surface of a 3-dimensional ball. And if you have attended my Geometriekalküle lecture, you remember that we had this picture of projecting the projective plane onto a sphere through the origin of the coordinate system from the standard embedding, and there points in the real projective plane ended up as pairs of points on the sphere. So essentially, each point here was identified with its antipode. And so what you get here is geometry on a sphere where you identified antipodal points. So this is almost spherical geometry up to that identification, and the proper name you should assign to that is elliptic geometry. So whenever you hear elliptic geometry, it's essentially geometry on the surface of a sphere with antipodals identified. So what do we take next? So we understood that point. So as a next point, let's jump to those 2 cases. Well, they are essentially the duals of the situation that I have here. And if you look at the table, they have to fit into those 2 fields of the table. And indeed, this one here fits here, where you have a parabolic measurements of angles. So you see you have a double tangent here, both hitting at this one point of intersection, but you still have a hyperbolic distance measurement, because whenever you take 2 points and their joints and intersect it with the fundamental conic, you get 2 points, and these 2 points of intersection give you a hyperbolic distance measurement. And take the brother at the other side, which is this one here. It's essentially the same situation where now you have an elliptic measurement of distances and a parabolic measurement of angles. And you see, I went pretty far over those cases. The reason is we don't want to dive into those cases too much, but I gave you the names here. So essentially this here is something like a dual Euclidean geometry, and this here is dual pseudo-Euclidean geometry. So relativistic geometry is also sometimes called pseudo-Euclidean geometry. So now it gets interesting once more when we come to that case, and you see I have 3 cases left up here, and in a certain sense those 3 cases that are still left could only be understood in the framework of Cayley Klein geometries if you take them together, because they all correspond to the same situation here. And this is what we want to look at next. So essentially we will treat those cases all at once. But we will see that one of those cases plays again a special role and deserves further attention. So we have the fundamental conic, which is a non-degenerate real case in all 3 cases here. In each of these cases we will have the same type of primal and dual conic, which corresponds essentially to the unit circle. So what is the difference here? The difference here is where we actually place our objects, and I made the difference here on the situations at which we will perform the measurement. So let's look at this situation here first and consider 2 points that are inside the fundamental objects. Inside meaning that if you try to draw tangents from one of those points to the conics, you only get complex solutions. So outside would be that part and inside would be that part. Now take 2 points inside, take the join, and you see you get 2 real intersections no matter which points you take, and this corresponds to an hyperbolic distance measurement. And for the lines, consider 2 lines that intersect inside the conic, and in that case you will get, well, there are no real tensions from that point to the conic, and so you get an elliptic angle measurement. So if as well the lines intersect inside and the points that you considered are inside, then you end up in the situation of angle measurement elliptic and distance measurement hyperbolic. And now let's move to other positions here. So let's for instance consider the situation where we have an angle measurement of 2 lines that are such that their intersection is outside the fundamental conic. Then you get 2 real tangents, and then you get a hyperbolic measurement of angles in that situation. And also in that case you should only consider lines that intersect outside. Now we have to talk about distance measurements. So in that case, if you perhaps focus on the outside of your conic here, you may measure the distances between 2 points that are such that their join meets into real points, or you have 2 points such that their join has only 2 complex intersections with a fundamental object. And you see, this is all a little bit artificial, and you really should consider those 3 cases as one situation of the Cayley Klein geometry that corresponds to the real non-degenerate case. You see, you can somehow switch between the different types of measurements depending on where you do your measurement. So now comes a big but. But one of those cases is special. And now I want to imagine that you are a being living in those worlds here. And this being living in that world can only walk around in that world in finite steps. So assume that you are inside the fundamental conic and you walk in finite steps. There is no way for you to get from the inside of the conic to the outside of the conic. So in a certain sense, you are trapped in the inside of this conic. Similarly, if you live in the outside, you are trapped at the outside. So there is no way from the outside with real distance measurements to get from the outside into the inside of that conic. So either you are out or you are in. And now let's focus on that point and assume you are a being trapped in the inside of that conic and you are doing geometry in that world here. And if you're doing geometry in that world here, you may want to intersect lines. But you only see the intersection if these lines intersect within your world. You cannot see an intersection like here that is outside. So you only get real angles between lines that really intersect inside your fundamental object. So in a way, if you focus on the situation that is entirely inside here, and you are a kind of two-dimensional geometer living in that space, it totally makes sense to speak about this situation inside that conic as a consistent kind of universe. And this universe is actually called the hyperbolic plane. And we will come to that to way more extent later on. And so very often these types of geometries, when they refer to non-degenerate real conic, is simply called hyperbolic geometry, where many people will implicitly say, well, and if you do this kind of geometry, it makes sense to make only measurements between points that are trapped inside your fundamental objects. But we see from the viewpoint of Cayley Klein geometry, it totally makes sense to take these three cases together and consider them as one case. We will spend our entire next lecture week in understanding what is going on in that case, because it is historically also extremely relevant, because it resolved 2,000 years lasting conflict of geometers trying to understand whether Euclid's axiom of parallels is independent from the others or not. And so hyperbolic geometry can be considered as one of the starting points of modern mathematics, and I will come to that with a really extensive discussion in the next week. So, you see, I spent almost all the lecture explaining one slide and all the connections, and you see also how these puzzle pieces here fit together smoothly in these different worlds. So, talking about fitting together smoothly, I want to end today with an animation that should give you a kind of dynamic image of how different situations here are related. And for that, I want to analyze the following situation. I want to fix a primal and a dual conic, and I want to study circles. So circles being defined by a center point and by a point on the perimeter of the circle, and circles are the set of all points Q such that the distance of the center to both P and Q is exactly the same. It's like how you would define a circle in usual geometry. Take a center, take a point on the parameter, and take all the points that have the same distance to this point. And I want to show you what happens in Cayley Klein geometries if we study circles, and perhaps you will be a little bit surprised how rich that world is. Here, let me start with the case of hyperbolic geometry. So here you see the fundamental object, and here you have 2 points. You have a point M, which is the midpoint of the circle, and you have the perimeter point, which is, well, one point that defines how big the radius of your circle is. And so the radius is exactly the distance from here to here, and everything pretty much looks like a circle. Let me now move around the points, and I'm now in hyperbolic geometry, and I have the primal dual equation for the unit circle here. So if I move my point here and I move closer to the boundary, you see that the circle doesn't look like a circle at all. It looks like an ellipse, but from the perspective of Cayley Klein geometry, it is really a circle. It is the set of all the points that have the same distance to the center of the circle. And you remember, distances, when they get close to the boundary, they get squeezed together. And this is what we actually observe here. You also observe that if I move my point close to the boundary, I get a bigger and bigger circle that more and more corresponds to the unit circle. So let me move on. What's happening next? Let me, as a next situation, move my center of the circle outside the fundamental object. And let's see what happens. And you see what happens is this here. And you may wonder what that picture here means. Well, it's just the algebraic solution to what I just explained to you. You have the center of the circle here, you have a perimeter point here, and essentially this is the set of all the points that are at a position that has exactly the same distance to the center here as your boundary point has. So it's just a solution to an algebraic equation. And we get that solution, but you also see a little bit structure. You see that this circle is tangent to the fundamental object at 2 points. And so actually, even if our conic is, even if our circle is such that the center is inside the fundamental object, also this object here has 2 touching points to the fundamental object. You just don't see them because they are real. So let me go to that situation here again, and let me make one more remark for that situation here. Well, imagine again that you are a being living in that world, and you walk along your circle in unit steps, and you want to get to the other side while walking along the circle, and you see you cannot get to the other side because one part of the circle is really infinitely far away from you. That's a very strange situation of measurement on a circle itself. So last case, let me take that point and move it to the outside, and then you see if you have a point and a point at the outside of the circle as of the fundamental object as perimeter point as well, what you get is something that doesn't look like a circle at all anymore. You have a kind of hyperbola, but algebraically it's still the corresponding circle in Cayley Klein geometry. It's a locus of all the other points that have the same distance to your center of the point as your perimeter point. So let me move these points to the inner part of the circle again, and let's now make the next experiment, and let's make walking in unit steps. So walking in unit steps can geometrically nicely be constructed by well, a chain of circles. So this circle here has a certain radius defined by the distance of these 2 points here. And if you make now a circle through that point around this point here, then you get a circle of identical size in Cayley Klein geometry that goes one step further. And you can make our construction of walking in unit steps by such a chain of circles. And what you observe here, if you walk in unit steps, you get closer and closer to the boundary point, but you will never surpass it as we have it in hyperbolic measurement. So let me do a few other experiments. Let's take our 2 points and put them outside the circle. So let me go to this situation, and you see also here with our kind of hyperbolas that we get as unit circles, you will in a certain sense get closer and closer to the boundary point but never surpass it. It becomes interesting if we go to a situation, let me move that perhaps down here, where we have a situation where this line does no longer meet the fundamental object, because then we will have an elliptic measurement of distances, which means that if we go in unit steps, we will make further and further steps and eventually come back from the other side. So I might try to move that to some kind of special position, like say here, where you really see you now have really rather big angle, and in that big angle you go get bigger and bigger and come back from the other points. I should mention that these pictures that you get here look extremely aesthetic. So I'm really surprised on how the aesthetic these images are. Let me do one more experiment, and this time let's not make a chain of circles, but let's make a sequence of concentric circles. So here is a sequence of concentric circles. I used the same chain of points that I have here to construct a sequence of circles which have increasing radii starting from my center here, and you see what happens if both points are inside these chain of circle, just also stays inside the fundamental object and does never surpass the boundary. Yes, so let's again move the points and see what happens. So let's move my interior point at the center to the outside, and let's move the other point to the outside as well. And you see what I get is a kind of chain of hyperbolas, which are circles in our world, and for the elliptic case, situations will look like that here. So you see concentric chains of circles really look like, well, kind of circles that meet at some point here at the boundary. So also here these concentric chains of circles also will have a kind of touching point to the fundamental object. You just do not see it. So now let me switch back to the chain of circles, and you see I still can do more things in my animation. I can move this slider here and change the parameter of my primal dual conic. And now I put the primal dual conic into a situation where I put this parameter alpha, which can run from minus something to plus something in my animation, at places such that if I put alpha to be -1, I'm in the hyperbolic case of the unit circle, but all these cases here are projectively invariant, and here's the corresponding picture for the corresponding equation for the dual circle. So why am I doing that? Because now I have the possibility to make alpha even positive and make a smooth transition from hyperbolic geometry to elliptic geometry. And let me first go very fast from here, hyperbolic geometry to elliptic geometry. And what you see here now is a chain of unit circles in elliptic geometry. So you see they get larger and larger, come back from the other side and approach again our point that we had in here. And I made this transition pretty fast on purpose because I want to show you what happens if you do it slowly now. So let's again go back to the hyperbolic case. So once more, if you are in that situation, you have essentially a minus minus plus signature for the primal conic, and in that case you have a plus 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 signature, so you are in the all complex case. And in between lies the Euclidean case, and let me now go to the Euclidean case, and you see if you go to the Euclidean case, so it's here, so you just get what we in our usual Euclidean geometry would consider as a proper chain of circles in one direction. So you could take a ruler and a compass and just create this chain of circles on your desk at home. But you also see how smooth this transition is. So you see here I actually formally I need the degenerate measurement, and but if I do it, it's almost invisible how you get from this situation to the Euclidean situation, and how you get from there to the elliptic case. And in a certain sense, this represents a fundamental dilemma in our universe, because we will never be able to tell if we really live in a Euclidean space or in an hyperbolic space or in an elliptic space, because we can do measurements only up to a certain epsilon. And if you look at this situation here, they are almost indistinguishably close together. And let me now, I should also show you the picture of the, well, concentric circles. And if I move out to hyperbolic geometry, you see also you almost cannot tell it apart whether you're still in the Euclidean case or not. And the same for the elliptic case. So this looks like a tunnel that you get here. So for the elliptic case, it's also very close to the Euclidean case when you are nearby. But in the elliptic case, if you, well, continue and make it more and more extreme, you see essentially you get situations where kind of shadow circles bounce back from the other side of the geometry. It's like making circles bigger and bigger on a sphere, and then at some point they go to the North Pole and come back from there again. And so I think I gave you an impression of what's going on. I just want to show you one more situation. In the elliptic case here, if you go to more extreme positions, this really can get, well, such that, well, you get, for instance, pictures like that where the circles really circle around, and here you get some kind of circular interior that you won't be able to reach with your circles. Here you see it gets really geometrically involved. So I hope that you can appreciate two things here, that you can appreciate the mathematical consistency of the whole system and how nicely these different kinds of geometries work together on the one hand, and that you also can appreciate the aesthetic value of what we're doing here, because you get very, I would say, harmonic pictures of chains of circles that arise from considering different kinds of geometry. In our next lectures, we will do three things. So in the next lecture, we will once more consider the aspect of transformations in Cayley Klein geometries, because there's one important message that you still have to get to know. Then we will do a little bit elementary geometry in general Cayley Klein geometries, and after that we will in the next week make a really extensive excursion to the case of hyperbolic geometry. See you there!